All right, and with that, I guess we'll get started here, everybody. Good morning, almost afternoon. I'd like to thank everybody for joining Rumsey for our ongoing locked-in series being hosted by Rumsey specialists, or in this particular case, a special guest that we're bringing online. My name's Sean Huber. I'm one of the automation group specialist managers here at Rumsey Electric. Today, we're focusing on the power side of our business and putting together the presentation here with our guest speaker for correcting harmonic distortion and active filters. MESTA as a company and with Jim's help, who he'll talk here shortly, has been a good partner of Rumsey's for the past few years. I feel that they have a differentiating product that can help fulfill IEEE-519 or just general power quality requirements. What I will also say, and I think Jim will probably talk a little bit about it, is that MESTA is a tool in the toolbox. It's not the only answer for power quality issues. So from a Rockwell perspective, we have active front end drives with the 755 TL. There are passive filters for certain applications, and a lot of this stuff really depends on the very specific application that you're trying to meet and how much power you're actually trying to put out. So all of that can, you can ask those questions here, or obviously follow up after the presentation itself. I've directly worked with Jim and MESTA over the last few years, and we've had some pretty good success at a couple of relatively large pumping applications. And that's part of the main reason that we've asked him to be the special guest and present to everybody on this call. So with that, Jim, assuming everybody can hear you, I'll turn it over to you and go ahead.
Okay, perfect. Thanks, Sean. And yeah, thank you again, everyone, for your time today. As Sean said, we'll be talking about harmonic distortion and active harmonic filters. Just as a little background about me, I've been working with MESTA Electronics for the past 6 years, specializing in power quality equipment. And I'll tell you, we've been working with Rumsey, as Sean said, for a few years now with some good success, being able to help those customers meet IEEE 519 requirements. Just as a little background about MESTA Electronics, so we're based just outside of Pittsburgh, PA, so just the other side of the state, not too far. We've been manufacturing equipment. I started with UPSs in the mid-'80s. We started as a consulting company in the late 70s. Our senior engineering team and our founder were all ex-Westinghouse guys. If you worked in power and you were from Pittsburgh back in the day, you were a Westinghouse guy. So one of the many split-offs of that company when that was falling apart. We started then getting into induction heating power supplies in the mid-'90s, early '90s, and that's with a very niche market for crystal growth, for the semiconductor industry, and fiber optics. So very, very specialized, trying to heat very small crucibles up several thousands of degrees Celsius and maintaining that temperature over days and weeks without more than a couple degrees change. And then that got into, in the late 90s, 1999 was our first active filter application. All of our equipment's made in the factory outside of Pittsburgh, so all made proudly in the US of A. We've been working with Rockwell Automation for quite some time. This is actually how we got involved with Rumsey, through the Rockwell Distribution Network. We've been an Encompass partner since 2006, their first active filter partner. All of our equipment's been tested at their Mech 1 Drives facility. Several of the pieces of information I'm going to talk to you about throughout this presentation, we actually learned from their testing as they were comparing us to other filters in the marketplace. All of our equipment can be directly put into Rockwell MCCs or in standalone applications. And that being said, even though we pair very well with Rockwell drives, we can work with any other VFD manufacturer. Rockwell has some unique advantages with their input, their DC choke that they have that we can utilize with our filter. But again, we can work with any variable frequency drive. We know a lot of customers that we have a mixture of drives in their facilities, so that's not a problem for us. speaking back to that first active filter that we put out in the field, it was actually for an induction heating customer. They had 7 of our inverters, and they were using the voltage waveform as a reference for a significant amount of laboratory equipment, and our inverters were obviously distorting that waveform. So they said, "Oh, what can you do? What can you do for us?" And that's when we came with our design. And it's actually still running today, hooked up to a phone line, because that's how it was back then, getting all the information off of it that way, before there were fancy displays that we have now. We have hundreds and hundreds of these out in the field, and we service multiple different markets. Most frequently, we find ourselves in municipal projects, water, wastewater, Department of Transportation, those kind of projects. But we also find ourselves a lot in oil and gas, mining. Around our area in western Pennsylvania, we're in several different natural gas and mining applications. And then also, depending on the region, we find ourselves in all sorts of different manufacturing projects. Although many of you don't work out there, our favorite state is actually Idaho. Every single project that they put out, whether it's beet processing or dairy or who knows what, they have to meet IEEE 519, and the utility companies don't just fine them like they do around here, they'll actually shut them off. So we're very involved with a large number of projects the further west we go. And a big part of that is because of the excess power distribution that we have in the Northeast compared to somewhere like Idaho. When something new goes out in the middle of nowhere, the harmonic distortion that's coming out of that facility will negatively affect everything along that run, all the way to the power company. A big part of that is because they aren't designed with the excess distribution that, like especially around, a good example around Pittsburgh would have, because of all the capability that's still around, even though all the factories had left. So then we're going to spend some time now talking about some of the problems that result from harmonic distortion, then get into active harmonic filters specifically and how they compare to other mitigation techniques that are out there. Because as Sean said, we are a tool in the toolbox. You'll find that as we talk, the quantity of drives, the total amount of horsepower, the size, how much room you have physically will help determine which option's best for you. So we'll start off with IEEE 519, talking a little bit about all the other main problems that you'll see with equipment wiring overheating, malfunctioning in equipment, and power factor correction capacitor failures. So what is IEEE 519? I'm sure many of you are familiar with this power quality specification, often found again in water, wastewater, and municipal projects, but we see it getting enforced more and more across all industries. The most important piece of information from the 2014 rewrite that happened compared to the 1992 was that they clearly defined the point of common coupling. It used to be there was a lot of ambiguity. Do I have to meet it at the load? Do I meet it at the MCC? Do I meet it at the facility? And every manufacturer that had a certain product would say whatever fit their needs best. And that was one of the reasons why 18-pulse drives were very popular, because Robocon was very effective, saying we can correct for this right where our load is, and we'll definitely be okay all the way up through. But now the point of common coupling is clearly defined as where the utility meets the facility. So it opens up the playbook for all of you when you're in design to say what's most cost and what's most space effective for me here. Is it at the load, or is it at the MCC, or is it at the switchgear? And that opens the door very nicely for an active filter being able to correct for all the loads that are downstream of it at one point. A couple other changes that happened with 2014. So when we're looking at these charts and tables, we're going to go to the next one first actually, with the current harmonics. It used to be that depending on what percentage you fell into, trying to determine this was a little bit more complicated. What kind of process were you? Hospitals had to meet 3%, certain manufacturing met 7 or 9%. Now it's clearly defined to say you fall into a band depending on the maximum short circuit rating of your utility transformer and the total demand load current that you have. And this is something that we can help you to do. I'm sure Ramsey can help. We can all take a look at any information you have to help try to find what band you fall into. But active harmonic filters are designed to meet that 5% spec. And anytime you start to look outside of 8%, an active filter would probably be more expensive than because it would be providing more correction than what you're needed as per the utility requirements. And active filters in general and passive filters are designed to stop that current distortion, because current distortion causes the voltage distortion. When we're meeting that 5% specification, then we're also going to be meeting this voltage distortion limit as well. They also raised the voltage distortion limits for many customers from 5 to 8%. Most of the times when you're looking at the applications that we work with, we're falling in with the 5 to 8% requirement there. Some of the other problems that we see when we're looking at harmonic distortion. So most of the time you're going to be looking at an active filter, again, is with IEEE 519. But as more and more facilities, are increasing their total number of nonlinear loads, we see more and more problems occurring. So one of the more common ones is equipment overheating. And this is a big reason that this happens is we have the high frequency current that those VFDs are now sourcing is traveling through the wiring, traveling through transformers, and all of that's effectively pushing to the outside of the cables. And so we're not using the parts of the cables that we're supposed to, and that's why VFD cable is very important to look into when you're working with VFDs to help try to mitigate this. But you have skin effects, so all of that high frequency current is being pushed out to the outside of the wires. And then when you have multiple windings together, you have proximity effect. So you have that basically on steroids. It's compounding upon itself, that problem, as the high frequency current's moving further and further out. And then, I already kind of mentioned this again, and this will help to decrease your overall system capacity because your transformer is designed to have a certain amount of current go through it, or the generator is designed to provide a certain amount of current, and now you're providing all of this reactive high frequency current that you weren't originally designed for. Additionally, we've seen a lot of applications where power factor correction capacitors have failed because of VFDs. So like all capacitors, they are basically a well for that harmonic distortion to fall into. They'll keep calling for more and more of it, and more harmonics will go to them until they become less effective and fail. So it's always something to keep in mind, because power factor correction capacitors are a great tool to use whenever you are trying to correct for linear loads, but you'll just want to make sure you have something in between any VFD loads and these power factor correction capacitors. That'll help to protect them, and so that, for example, we could do what we're best designed for, correcting for that harmonic distortion, and then they can correct very cost effectively for the power factor for any other linear loads that are in the system. So what can an active filter do for you? If you're not familiar with active filters, we're designed, again, to meet those IEEE 519 recommendations, meet that strictest standard of 5%. The biggest differentiator between us and other harmonic mitigation techniques is that we can correct for any number of loads downstream of us. So one active filter on a lineup could take care of a whole MCC or potentially take care of a whole facility. In addition to correcting for harmonic distortion, we can correct for the power factor as well, and we can balance the three phases. And I'll talk to you a little bit about the relationship between being able to correct for all of those at once and some of the cost savings that they provide. And again, as we had just talked about, being a complete solution from a facility start all the way down to the load. So how do we work? So active filters are using a set of current sensors on the line, and we're continuously monitoring the load, and we're trying to see exactly what current those loads are trying to source for. And during the waveform, and this is a look at a simplified single phase version of it here, we actually take in energy, converting AC to DC, storing in our DC capacitors during parts of the waveform that are correct, and then we deliver all of this high frequency current downstream for the VFD loads so that the utility or the generator doesn't have to provide it. And we'll look at a more detailed example of an installation diagram a little later on, but here's a look at how the active filter would be set up. So the active filter is installed in parallel, and there's a couple of unique advantages to that parallel installation. So first, being in parallel, we only need to be sized for the corrective current required. So a good rule of thumb is harmonics are about a third. So if you have a 900 horsepower worth of VFD load, you might be able to correct it with one 300 amp filter. Doesn't matter the number of drives to total that 900 horsepower of VFD load, but that's a nice cost savings that an active filter can bring you. And additionally, being installed in parallel, probably most importantly for many of our customers, is if there's ever a problem with the active filter, the process does not stop. So because it just is that there'll just be harmonic distortion for the day, the days, the years that the active filter just happens to be off. So it's a really nice tool for water, wastewater, or any critical application that you don't have to be concerned that, okay, we'll just have some harmonics until the active filter is back up and running when we get MESTA back out there. As you can see here, we use a set of 2 current sensors normally, and we can calculate for the third CT, the third phase there. We only need a third CT if there are any single phase line to neutral loads downstream of it. For example, if there'd be lighting loads that aren't separated by a transformer. Normally those are separated though, so we can stick with using 2 CTs. So here's some actual test data from our active filters operating. As you can see here, this is a lot more severe than what you'd see out in the field, but on the left here you see a very distorted double humped bridge, like pulse width modulation, looking much like a 6-pulse drive would, except here we see upwards of 70% THD with a poor power factor. Here we see the injecting current that the active filter is putting into the line, so it's the net canceling current, and then the resulting sine wave that's upstream of us. So you can see being corrected below 3% and correcting that power factor to unity. So we were originally designed with that hospital specification in mind, the old one of trying to be below 3%, but we can definitely meet the 5% specification that's out there now. There's a very unique advantage for that corrective capability you saw on the last slide, is we are the only active filter that does not require the use of line reactors if the drive has a DC choke. So this is why we work very well with ROCKWELL and their PowerFlex 750 series drives, because with that DC choke that they have, it allows the designer to say, what do I have room for? Because line reactors are very good for the VFDs. I'm sure many of you are familiar with protecting the drives against line transient events, helping if there's oversized transformers, stuff like that. But oftentimes we get called in and we have to meet IEEE-519, and there's only so much space. So we can help to deal with that with less space, because you don't have all those line reactors being used. You normally again see the space savings when you have a large number of VFDs. You normally want to take a look at an active filter if you have 3 or more drives totaling at least 150 horsepower. And we'll talk about that a little more in depth as well. Then we talked a little bit about the power factor correction. So because of the vectoral relationship between out-of-phase linear current and harmonic distortion, we're able to do more with less. So with this little example of 75 amps of harmonic current and 50 amps of out-of-phase linear current, if you were to correct for them separately, let's pretend you had 75 amps of passive filter correction on the VFDs and 50 amps worth of power factor correction for the linear drives, you'd have to correct for 125 amps of correction. But because of the square root of the sum of the squares, when you put those together, you'll see it's only 90 amps of correction that are required. So you got a 100 amp filter. Wouldn't be much of a cost savings in this small example, but you can see how it could add up over the course of a whole facility if we're being put at the switchgear. We always like to spend some time talking about the testing of our units and also how we're different from older active filters or other brands you might be familiar with. So just to look at this little drawing, we have our active filter with our CTs. We have a load simulator we use, and with that load simulator, we are ramping up and down like a VFD would. We're initiating step load changes. We're making sure that we're responding within a half a cycle. So right up industry leading half a cycle response time. But at the same time, to eliminate many of the problems that older active filters had, was we have a slow integration control to make sure that we're not only predicting what we think the VFDs are going to do, we're waiting for that to actually transpire on the line. Older active filters used, part of not being digital, had to use the predictive side of harmonic distortion a lot to try to be able to keep up with the VFD loads, because harmonics are a predictive anomaly if you ramp a drive up from 0 to 100, but oftentimes that's not what was happening in the field. Drives were going up and down and all over, so they would be injecting other current into the line, causing some line instability. So that's something that we make sure we don't do anymore. Additionally, with this testing, we do current limit all of our equipment. So all of it's designed to say, if I'm a 100 amp filter, it'll output only 100 amps of correction. If loads are added later on, and now there's 110 amps of harmonic distortion out there, the active filter will just provide 100 amps, and it won't cause any problems to the filter. Older active filters and some other active filters that are still out there now, they'll have device failures because they'll be trying to output as much power as they think as the system needs, which ultimately causes their IGBTs or other whatever devices they're using to fail. Another unique MESTA feature is our high operating efficiency. So we have the highest operating efficiency in the marketplace with 98%. This allows for significantly less airflow for our units, and we have our cooling requirements are a lot less. And it helps some of our larger panels be quite a bit smaller than other guys out there. That's a 300 amp panel there, and it's only 27 inches wide, which means our NEMA 1 300 amp unit is actually smaller than many panels that are out there for other manufacturers. And with that efficiency adds direct operating cost savings to the customer. So we have a good little example here with a 300 amp unit, ours being 98%, the next closest guy out there being 96%, running max load all year round, and there's just a little to say, oh, what's my kilowatts cent per hour? And some of you may be familiar with what you have, but you could be saving just from $2,000 to $4,000 if you fall within that band. We know some of our customers actually have higher costs than that, and you can see that add up a lot over when you have multiple filters in the facility, and it helps us to have a very long mean time before failure, being over 200,000 hours, something we're very proud of. And a big part of that is because of the thermal stress range that we're not subjecting our equipment to by having that higher efficiency. And then to look at how we're configured, how do you normally get an active filter? Pretty industry standard, 50 through 300 amps. All of these are available in open panels, and that's what we provide with ROCKWELL putting in their MCCs. But more frequently, we're in NEMA 1 enclosures. These then are using a feeder breaker in the MCC or at the switchgear they're cabled over to. Again, 50 through 300 amps. We can parallel multiple units together to achieve higher current ratings. So if you need 600 amps of correction, you put together two 300 amp filters, etc. We then also have other enclosures available upon request. We work with some local integrators that install our equipment, UL, and any kind of enclosure that you might require. We understand that we sometimes end up in dirtier environments, or oftentimes we actually end up outside. And I'll talk to you a little bit about that as well, but going into NEMA 3R and NEMA 4 enclosures for that. How do you communicate with us? So we have a front display I'm going to show you some pictures of. We have control status relays that you can use as well, and then you can also communicate with us over Ethernet to also enable and disable the unit. And we have Ethernet IP connectivity and a new add-on profile with Rockwell, and I'll show you some pictures of that as well. So here's a look at our operating screen. As you look through this, you'll see we're pretty much a full power monitoring device. So the load column is before correction and the line column is after correction. So you'll see this is a 100 amp filter correcting from about 67% THD down to 4%. And you see the RMS drop in current from 150 to 115. So that's all that reactive current that we had talked about earlier that was being supplied by the generator or the utility, that was traveling through your transformers and through your cabling, that now isn't happening. So that's that increase in system capacity. And you can see kW, kVA, power factor, and the percent loading. And if I don't have it on here, but if you would click that More button down there, you'd see a biphase breakdown of all of this information. And the menu screen, we'll look at a couple of other images as well. This is our CT setup screen, and this is probably our favorite feature that is unique to MESTA. We have a very battle-tested function here. So if you've worked with anything with CTs, you know there's just a bunch of ways for someone to install them incorrectly. We think it's a game. Which way do the arrows go? What phases do they need to be on? And everybody seems to pick wrong. But we have, the system tells you how it's set up. If it's set up for 3 CTs on the line side of the filter, and it'll tell the customer if they've done it correctly or incorrectly. If it's incorrect, there'll be a different number here, a brief description. With that number in the manual, it gives a very specific way to physically change the wires or change the CTs to meet the error. Or with most options of error, a green button appears here that says automatically adjust. So the unit, for any option of error with 3 CTs, for example, can reverse polarities and redesignate phases all on its own. So we've had times when a customer can't get to the CTs, and that's actually how this came to be. We were working on a project with Rockwell, and the integrator that they had used said, "Oh, we know what we're doing. We're going to use solid CTs. We always recommend split core CTs so that they can be moved if there's a problem." And they said, "Oh, then when it was installed, they said the active filter is not working." It's like, oh, geez, okay, well, what can we do here? And we were reading, a negative power factor, all sorts of erroneous information, and we're like, okay, the CT's got to be wrong here. And they said, oh, we actually can't find the CTs. We embedded them so deeply in the bus work of the MCC, we can't get to them. We're going to have to take it apart. What can you guys do? Must have already been working on this at the time. I guess it was about 5 years ago. Our engineer went out there, flashed the unit, and it was able to determine that 2 CTs were on the line side, 1 was on the load side, and 2 of them were flipped the wrong way. An option of error we hadn't even thought about, and the unit was able to automatically adjust for that, so they didn't have to take it apart. So again, extremely powerful tool. We have a historical database. All this information is available from the front display or over Ethernet, and then we also have a USB port on the front of our unit that you can put a flash drive in and download the information with a click of a button on the front display. If there's ever a problem, you can send that to us and we'd be able to take a look at all sorts of information. I don't have it all on here, but for example, with this time-stamped 500 on-off events, we have 1,000 reset events. We have what we call flight data recorder information that we use to make different waveforms to be able to evaluate internal and external information to the filter. And again, with this example here, looking at the instantaneous and the RMS values to really get a full picture of what's going on. And then a quick look at something we're very excited about to have just happened at the start of this year, was becoming a connected partner with Rockwell Automation. We're their only active filter partner that has an add-on profile. So with that, if you're not familiar, the add-on profile is something that you're able to select over Studio 5000 and RS Logix whenever you're using an intelligent motor control center. And what it does, you can select MESTA DPM active filter, and it'll auto-populate 51 different data tags for you so that you can not have to deal with all of that when you're integrating the unit into your system. We can also communicate over a device-level ring network, and we are equipped with address conflict detection. So if there's ever a time when multiple pieces of equipment are given the same IP address, we can help to determine that problem and reassign an IP address. So this is a look at the kind of information that's shown over Ethernet IP. Again, all the information that you were looking at on the front display. You see the line voltage, line amps, harmonic distortion, percentage, amps, all of that. Again, auto-populating all of that for you. And that falls right into how easy we are to start up a commission. Something that was very different from older active filters and many active filters that are out there now. First is that as long as the filter is about 15% loaded, that's enough current for the CTs to read to make sure they're going the right direction. And the unit will then respond automatically with the changes in loads. Older active filters needed to be, loaded and tuned to certain loads, and that's oftentimes with many different types of passive filters being tuned to certain frequencies. So when the active filter is turned on and there's a little bit of load on, they just go to that CT setup screen. If the CT setup screen says they're good to go, they just hit run. So nice and easy. Quick Start's 7 pages long, and the first few pages are warnings so that you don't shock yourself. So real easy to use. A lot of happy people there. And then with the Ethernet IP connectivity and that add-on profile, putting it into anyone's logic is very, very simple as well. So, as Sean had said, and I had said earlier, being that tool in the toolbox, we like to talk about how we compare to active front-end drives and 18 pulse drives. 18 pulse drives are a much older piece of technology, definitely tested, very large. That's usually one of the bigger issues with them. They take up a lot of real estate. Many drive manufacturers, have moved away from them to move towards the active front-end drives, like Rockwell has with their 755 TL drive. You're going to want to look at active front-end drives or 18 pulse drives normally when you have a smaller quantity of loads because of the amount of space they take up. Again, with the active filter, looking at 3 or more VFDs totaling at least 150 horsepower. What does that do for you when you get to use the active filter instead of one of these other drives is that you get to use those 6 pulse drives, which Rumsey has readily available on the shelf for you. If you have a problem, there'll be one with you again the next day. Meanwhile, the lead time for those other pieces of equipment are much longer, just like an active harmonic filter, except when the active filter goes down, as we said, the process doesn't stop. While if one of these goes down, your process would stop until you got a new drive. We can correct for other power quality issues and 18 pulse drives, and there's many different white pages about this, but 18 pulse drives struggle if there's a line imbalance present from the utility already. And that's often the case in the real world. So 18 pulse drives struggle more often to meet the 5% specification. And then active filters are really easy for retrofit applications. So if you have a wall space that you're upgrading or you're adding load to, active filter, not only is it small, but it can be put hundreds of feet away from where we're correcting. So you can knock a hole and put it in the other room, or you can put it outside in a different type of enclosure. It gives you a lot of flexibility. We have that happen a lot whenever a facility is not aware that they have to meet IEEE 519, and then they all of a sudden they need to, and bam, they put us outside to cover for it. And looking at the biggest cost savings that an active filter has over those others is if there are any redundant loads. So with water, wastewater, we see it all the time, but in many applications, we know the process can't stop, so you guys have extra drives sitting there that are ready to run if one goes down. So with this little example of having 4 VFDs and only 3 of them run, the active filter gets to be sized for just 3 of them, while the 18 pulse drive or the active front end drive, we'd have to have 1 for each of those loads. Good rule of thumb we've seen is 18 pulse drives are at least twice as big as their 6 pulse drive counterparts. So if you're looking here, we have 2, 4, 6, 8 space factors versus 1, 2, 3, 4, 5. So quite a bit of savings there for space and then for cost as well. Passive filters, just to keep in mind, not all passive filters are designed to meet that 5% specification. Always want to check into that depending on which band you're falling into. Great tools to meet that 8% spec. The one that we recommend most if you're trying to meet 5% is MTE, which is another ROCKWELL Encompass product partner. They have a great adaptive passive filter, they call it ADP, that are designed to try to meet that 5% specification. And they can handle being lightly loaded better than many other brands. But that's something an active filter doesn't have the same kind of problem with as passive filters. We can be extremely lightly loaded. You see there being as lightly loaded as 10% to meet that 5% spec. And other passive filters cannot do that. Will never cause a leading power factor, especially being unloaded. We always recommend if you're working with passive filters that you have that capacitor cut out to help mitigate for that problem of being lightly loaded and having a leading power factor. And just again, you normally see that these are less expensive options than an active filter, but if you have a large number of VFDs, you start to get into a lot of space constraints when you're working with a lot of passive filters. Again, just needing that feeder breaker, so you have 1 going in and out, nice and easy to connect to, and then the CTs on the line. This isn't too important, but just a reminder, you need those two CTs for the correction of 3-phase loads. We have line and load side CT installation. When you're looking at one filter, it doesn't really matter. All that means is you have the CTs upstream of the feeder breaker or downstream of the feeder breaker. The only time it really comes into play is if you have parallel installed active filters. So if you're able to put the CTs on the load side, you can share one set of CTs between all of our active filters down the line. Each of our active filters is independent. There's no master-slave relationship like some of the others do. So if there's ever a problem with one, the other active filters just keep on running like nothing's wrong. They only share CT signals. I'm going to pull up our sizing tool, and we're just about done here. Really easy when you're trying to size for an active harmonic filter. We just need to know the total horsepower that you're working with, if you're working with the drive with the DC choke, if you're working with line reactors, and what part of the band we're falling into, 5, 8, 12%. We normally would be happy to do this for you. We take a look at one lines and equipment lists all the time to say, what size filter do you need? You just click this, and bam, through a VFD lookup table we have here that with 455 horsepower using 3% line reactors, you have 149 amps of correction required. So we'd say, okay, you need a 150 amp filter. and then you say, Jim, actually I don't have room for the line reactors here, so I'm going to take them out, and I can get a new number, and I have 190 amps of correction. So now you have a 200 amp filter. The 150 and the 200 amp filter are the same physical size. There'll obviously be a cost difference, but that can be the kind of decision making that you have when you're looking at the design side. Be happy to, again, take a look at anyone's applications and using that tool with them for the first time. But just as a reminder of some of the things as we wrap up this presentation, is that the active filters are designed to meet that IEEE-519 specification and help to eliminate those harmonic distortions. We have extensive field experience, especially for your applications. It would be really easy for us to get anyone from the factory over to you guys. Very high efficiency, very easy to use with our CT diagnostics, and being able to correct for any number of loads downstream of us. Thank you guys so much for your time, and thank you to Rumsey for having me on. If you have any questions, feel free to ask. With the presentation, as Sean said, that gets sent to you after, we have a link for our product brochure, our guide specification, that sizing tool, and our Ethernet IP connectivity. You guys are all welcome to call or anything like that in the future to look at any applications, but I'll open the floor or if there are any questions now.
Yeah, thank you, Jim. Any questions anyone has around everything that Jim had laid out in front of us? All right.
Sweet.
Well, I will take it. Normally, I have something to input on some of your presentations, but I think you hit every one of the main topics, Jim. So I appreciate that.
Perfect.
So, all right. Well, hey, I want to, from Rumsey's behalf, thank everybody for spending your time. You will get a follow-up email with all the supporting documents and things like the Excel spreadsheet Jim was showing there. So you'll see all of that stuff shortly. Thanks for tuning in, and just as a general reminder, Rumsey will be continuing the Locked In webinar series every Tuesday and Thursday from now till the end of May. So just hop on our website and feel free to either look at the recordings that we have on the YouTube channel or sign up for any of the live ones where you'd be able to ask some questions. All right, with that, we will sign off. Thanks, everyone.